The live stream will work automatically this time.
Yeah, I'm sharing my screen in a second.
Mm-hmm.
I should share this. Almost there.
Okay. Yeah.
Yeah.
So then let me.
My slides. Sorry.
Yeah. Mm-hmm.
Okay.
Yeah, I guess we all can see it. Yeah, great. So today is the last meeting of PNS SoftMC where we will have a presentation. And during the following weeks, we will continue only with project updates, which will be off the live stream. Yeah, and today, only for today, we start at 5 p.m. But from next week on, we will keep, again, start the meetings at 11 a.m. again on Tuesdays. Okay, great. Then yeah, we can start with today's presentation.
Okay. Yeah, welcome everyone to the PNS course. Thank you for attending this talk, and I will present PiDRAM today, a framework for end-to-end integration of processing using memory. So this is some work that we developed, I guess, in the last 2 years, and then we have an archive publication of the work that I can share with you in the chat after my presentation. So yeah, I'll start with an executive summary. So we're motivated by recent works that propose in-DRAM computation primitives that have great potential to improve both performance and energy consumption of computing systems. However, these works are developed in limited environments such as simulators and characterization platforms, specialized characterization platforms like SoftMC. And in these platforms, many parts of the system are essentially ignored, of a real system is ignored. And then, therefore, the challenges in integrating these primitives into a system cannot be fully explored in these environments. And our goal is to develop a flexible platform to explore end-to-end implementations of current and future processing and memory techniques. And our key idea for this project is to build an FPGA-based infrastructure that supports in-DRAM operations and also system software. So this is the outline for the talk, and I will start with a relevant background on DRAM. Some of you will recognize this from last week's presentation. I'll use the same set of slides to remind you what DRAM looks like. And you see here a memory controller in a processor. It communicates with a set of DRAM chips on a DRAM module through what's called a DDR interface. And inside each chip, there are multiple banks that share the same chip I/O. And a bank is made up of multiple DRAM subarrays. And each subarray has a set of word line drivers and sense amplifiers. And in each subarray, there are multiple mats. And inside a mat, the DRAM cells are organized in a 2D array manner. And we refer to a row of DRAM cells as a DRAM row. And you see here a simplified diagram of a DRAM cell. And we will see how we access this cell. And again, this diagram shows how a DRAM cell is connected to a sense amplifier. And the cell contains two components. One of them is the capacitor, which stores charge. And the other one is the access transistor, which determines if the cell is being accessed. This access transistor is controlled by the word line. And we enable this to connect it to the bit line, to the cell to the bit line. And the bit line bar will essentially be the inverse of the bit line. And the sense amplifiers then enable signal to determine if the sense amplifier is currently active. So how we access the cell, initially both the access transistor and the sense amplifier are disabled, and both ends of the sense amplifier are maintained at half VDD. And in this example, the capacitor is fully charged. And to access the cell, we enable the word line, and this will connect the cell to its bit line, and the cell will share its charge with the bit line. Since the capacitor has a voltage level higher than the bit line, the charge starts flowing from the capacitor to the bit line, and this will result in the bit line voltage to deviate slightly towards VDD. When we enable the sense amplifier, it will compare the voltage levels of bitline and bitline bar and amplify the deviation until bitline voltage reaches VDD. And since the capacitor is still connected to the bitline, the amplification process will also restore the charge in the capacitor. And now we will look at how the DRAM device operates at the scope of a subarray. And because memory controllers typically access DRAM cells in the granularity of a cache line, we combine consecutive cells to form cache lines in the diagram in the green boxes. And on the bottom, we have a timeline of DRAM commands. So first we send an activate command to activate the first row. And then this will copy the data in the first row to the sense amplifiers. And at this point, we can read data from the sense amplifiers by sending read commands consecutively. And to access another row, we need to schedule a precharge command. And this will close the open row and set the bitline voltage to VDD, half VDD. We can now activate another row and we can read data from it the same way we read data from the first row. And to ensure correct operation in DRAM devices, we must obey certain timing parameters that define the intervals between DRAM command pairs. Again, two important parameters for us for this work is TRAS and TRP. So TRAS is the time required for the charge to become restored in the open, in the activated row. And we need to wait for TRAS before we send the pre-charge command immediately after sending an activate command. In TRP is the time it takes for a bitline to become pre-charged to half VDD, such that we can activate a new DRAM row. And between pre-charge and activate commands, we need to wait for TRP amount of time. I'll briefly describe existing processing using memory techniques that are relevant to us. So processing using memory techniques take advantage of operational principles of memory to perform both data computation, both data movement or computation in memory. And they exploit internal connectivity in the DRAM device, in our examples, to move data around. And they can also exploit analog computation capability. Some examples of these are these works that you see here. The first one is RowHammer. There's in-DRAM and then OR mechanisms, and DRange also generates true random numbers in DRAM. Here are references to these works, and I will basically describe this first work so that we get a better understanding. It's RowHammer. And I will describe the motivation of RowHammer using this animation first. So in a regular computing system, we have the DRAM device, and it's depicted on the right as the big yellow box here. When we want to copy data from this source page in the DRAM device to the destination page, we will first move data in blocks to the memory controller, to the caches, and then the core will retrieve the data and place or allocate a copy of it, and again in the caches. And this copy will be sent through this DRAM channel back to the DRAM device. And this channel, this communication actually is very high latency. It takes 1000 nanoseconds as reported in the RowHammer paper to copy 4 kilobytes, and also consumes a lot of energy, 3600 nanojoules to copy 4 kilobytes. And RowHammer's idea is to, basically the question explored in RowHammer is, can we do it in DRAM? Can we do this movement in DRAM? And they come up with this mechanism. So we already saw how a DRAM array was organized. And this is, you're seeing a subarray here, a depiction of a high level depiction of a subarray. So we have the source row and we have the destination row, and we want to copy the source row to the destination row here. What we do is we first copy the source row to the row buffer, and then we just copy it back to the destination row from the row buffer. So when we look at current DRAM devices and see how they operate, we already know that we can activate, by activating a DRAM row, we already copy its data to the row buffer essentially. But it's not clear how we can do the second operation, how we can copy this data back to a destination row. And here I will try to explain how that works. So this is basically over this animation, I will describe how RowHammer proposes to do this operation. So you see a source row here, a cell from the source row and a cell from the destination row, and also the sense amplifier and the bit line is connected to. So what we will do first is we will activate the source row and this will connect the cell to the bit line, and the cell will lose charge, share the charge with the bit line, and raise the bit line's voltage to slightly above half VDD. And then the sense amplifier will amplify this deviation in voltage. And then essentially, we have read out the DRAM cell at this point. So now the charge is also restored back to the capacitor. And now what we can do is we can disconnect this source row from the bit line. And then at this point, before we pre-charge the bit line, if we just enable the destination row, the data that resides in the bit line currently or in the sense amplifier will also be placed in the destination row. So essentially, we have copied the source row to the destination row over the sense amplifiers or over the bit line. And this enables fast bulk data copy with very small overhead. As you can see here, we only need to implement support for disconnecting the source row before the bit line is pre-charged. And the RowHammer paper explained this in more depth, how this can be done with very low overhead. And the second example I talk about is the in-DRAM bitwise operations. So we can support in-DRAM copy, all data zeroing and or not majority operations at low cost by using the computation capability inherent to DRAM devices. And our idea here is to activate multiple rows. And this can improve performance and energy by 30 to 60x. And this is also described in more detail in this paper, fast bulk bitwise and or in DRAM. I'll try to give a high-level overview of how this works. So this is a diagram we have similar to the previous diagram. This time we have 3 cells or 3 rows here because we want to do a majority operation. We activate multiple rows. So the initial state is the same. For rows A and B, we have initialized them with the value that represents VDD, and the bit line is pre-charged. So what we'll do is we will activate all of them together. When we do this, we're expecting the cells to lose or gain charge depending on their initial values. In this case, A and B will lose charge. They will share their charge with the bit line, and C will gain some amount of charge because the bit line voltage is higher than the capacitance of the cell that's connected to C. What happens then is there will be some deviation in the bit line voltage. We're expecting this to be closer or towards VDD because 2 of the cells that we activated were charged and the other one was not charged. So the majority of the cells were charged essentially. And then once we enable the sense amplifier, it will amplify this voltage deviation to VDD and write back the value, the majority of the 3, back to all of the cells. So you can see that the final state represented by the bit represented on the bit line is this Boolean function essentially. And when you simplify this a bit, you get this. And by setting the value of C to some constant that you know, you can realize either A or B or A and B operations. So now I'll move on to how these are done, these 2 operations in real DRAM chips. So Compute DRAM is a recent micropaper published in 2019, I think. It demonstrated this both bulk data copy and or operations in real DRAM chips. And the idea is to violate these 2 DRAM timing parameters, TRAS and TRP, and cause some sort of uncertain or undefined behavior in the DRAM device, and therefore enable these 2 operations. And you see the authors here, and there's a link to the paper on the bottom of the page. I will describe how this works over these 2 figures next. So first, I'll talk about how we do row copy. So you see a diagram, and then this diagram, basically you see the state changes in a single bit line that's connected to 2 cells in this simplified depiction. And on the x-axis, you can think of it as time, basically. So what happens is we first send an activate command to row 1 here, and this will cause the cell on row 1 to share its charge with the bit line, and the bit line voltage will raise slightly above VDD, half VDD. And then after waiting for a T1 amount of time, we will schedule a pre-charge command, and this will disconnect the source row 1, from the bit line. At this state, the sense amplifier was also activated, enabled, and then it sensed it amplified the voltage difference to VDD. So now the bit line in the sense amplifier has a voltage level close to VDD. And what we do then is we send another activate command. As the bit lines are being pre-charged, before it's completely pre-charged, we will activate the second row. And activating the second row will connect the cells on that row to the bit line. But the bit line is not at half VDD yet. It still holds the value of the previous cell that we activated. So we will essentially copy the voltage or what's represented on the bit line to back to row 2. So this is how compute DRAM works, or row copy using compute DRAM works. Maybe this is a good place to take questions if there are any. Okay, if not, I'll move on. Okay, so for more background or more details about processing using memory, you can refer to this lecture that Professor Mutlu has on YouTube, or you can watch a recent live, maybe this is not as recent anymore, but this was presented on October 27th last year. It's SimDRAM. It's another processing using memory substrate that was led by Nastaran and Geraldo in our group, and this could be a good thing to watch if you're interested in these works. And I have a link to the YouTube video below. So next, I'll talk about Rocket Chip, because this is relevant to the infrastructure we developed. So Rocket Chip is a open source SoC design generator, and it's composed of many component generators, system on chip component generators. And what generator means is essentially it's a piece of code that builds hardware. So so we have generators for processor cores, caches, and these are highly parameterized. So you can enable virtual memory, or you can enable different ISA extensions and generate multiplication and division units, place them in your core, or floating point units in a very easy way. And this basically, after we have this definition, this will output a synthesizable Verilog code that we can use to develop designs on FPGAs or ASIC. Basically, this allows us to build real system-on-chip designs very easily. Okay, next, I will give an overview of PiDRAM. So our goal, just to remind you, is to develop a flexible platform to explore end-to-end implementation of PUM, processing using memory techniques. And the way we do it is we enable we also want to enable rapid integration of new techniques via key components, and that will be more clear. So on the hardware side, we implement an easy to extend memory controller and an ISA transparent processing using memory controller. And on the software side, we have an extensible software library and a custom supervisor software that the users can easily hack and add new features to. So the first component, the memory controller, I'll talk about that and the motivation behind how we designed it. So when we look at current real processing using memory techniques, we see that they require issuing DRAM commands with violated timing parameters. And for that, we want to develop an extensible memory controller that facilitates implementation of new DRAM command sequences with violated timings through modular design. And therefore, by doing this, we enable essentially for users to implement new command sequences by only adding new state machines in the memory controller. And there are three submodules in the memory controller to further ease developer effort. And the first one is the periodic operations module, which takes care of periodic refresh operations and DRAM bus maintenance operations that must be done periodically for correct operation. A scheduler that by default just schedules regular read and write operations with a simple open bank policy. And the third component is what we call a configuration register file. And this stores all the timing information that we need to issue both regular DRAM commands and DRAM commands with violated timings that we use to perform processing using memory operations. And this is accessed by the CPU in the system using regular load and store instructions. The second component is the isotransparent processing using memory controller. And this is connected to the whole system as a memory map module, and hierarchically it's placed within the memory controller. And it has connections to many the other components in the memory controller, such as the configuration register file, scheduler, or those two. And I will describe this diagram in more detail in the upcoming slides. And we have a simple interface to offload processing using memory computations to the controller. We have a 128-bit large interface that we use to convey instructions from the CPU to this module and to ultimately perform processing using memory operations. And currently we implement 5 instructions. The first one is row clone. The second one, what we call activation failure, is access DRAM with reduced TRCD. We have another instruction to read random numbers from the memory controller, and another instruction to read how many random numbers we have available in the controller to ease the management of this random number generation that we have in the DRAM device. And another instruction to modify the configuration registers, basically. The instruction size we have is configurable, and we have many reserved bits, as you can see in this diagram, for other commands that will be implemented by developers in the future, hopefully. Next I'll talk about the software library. So we want to expose these operations to the user while abstracting all the hardware implementation details. And here's a function in this library that is responsible to perform the raw copy operation. So there are 2 stages here, essentially. First, we prepare the instruction in the first part of the code that you see here. We just fill the encoding correctly such that the source row gets copied to the target row. The instruction implies that operation, essentially. And then in the second part, we offload this instruction and block the execution until the command is acknowledged by the processing using memory controller. And by replicating these functions, the users can easily add new, they can easily expose new operations to the software. And finally, we have a custom supervisor software. And this is very simple, and it's an easy to hack operating system in one sense. That enables people to or users to integrate processing using memory techniques end to end by providing virtual memory management and also memory allocation. And this is based on the RISC-V's proxy kernel. And for future work, we'll leave integration of processing using memory lib into Linux, basically. Now I'll talk about the whole execution workflow of PiDRAM. And in this diagram, you see the PiDRAM's memory controller, and the modules is connected to. So there's a DRAM module. It also communicates with the Rocket Core RISC-V CPU we have in the system. So first, to perform a processing using memory operation, the user will call the necessary functions in the OS system. These are implemented as system calls, and then the OS will use the PUMOLib to convey all the information related to this operation, essentially the instruction to the hardware, using just store instructions, because the processing using memory controller is a memory mapped module, and it can be accessed by the CPU using load and store instructions. And then processing using memory controller will oversee the execution, meaning that it will control the execution of the processing using memory operation. And yeah, for example, we have row clone operations or true random number generation. And then the scheduler will arbitrate between either regular requests, processing using memory requests, and periodic operations. And for processing using memory requests, it will issue DRAM commands with custom timings that are placed, that are stored in the configuration register file. And finally, we have this prototype on Xilinx DC706 FPGA board. As the processor in the system, we have RISC-V CPU, single core, in order, clocked at 50 megahertz. It has a 16 kilobyte 4-way L1D cache and a 4 kilobyte instruction cache. And under this cage, there's a DRAM module that we use to perform computation in, essentially. Okay, do you have any questions so far? Nothing? Okay, so now I'll move on to and describe our describe one case study we did for row clone. So I'll start by describing its challenges to integrate row clone in a real system, the challenges that we have to face. First, it has essentially memory mapping requirements. The first memory mapping requirement challenge is what we call alignment. And basically, this dictates that operands must be placed at the same offset to their respective DRAM rows. So this, if we have this placement, we cannot copy source one to target one, because these pieces of data don't lie on the same bit line. So there is no way we can copy source one to target one, because they're offset at different places in the DRAM row. So basically, the bits in these two different chunks won't be connected to the same bit line. And the second one is granularity. So basically, operands must occupy whole DRAM rows. Otherwise, we wouldn't be able to make sure that we are overwriting valid data. So in this example, if basically the empty space in target 2's row is actually, if there's actually physical, like allocated data there, we will overwrite it with whatever there is on source 2's row in this empty space. So there could be useful data, and we will be overwriting it, and this is something that we don't want. And the third one is mapping, and this dictates that operands must be placed within the same subarray, so they cannot be in different subarrays, because otherwise there's no way for us to copy data using row clone the way I described it, full parallel mode, from one bank to another bank, or from one subarray to another subarray. And here you see the fourth mapping essentially satisfies all three requirements. The fourth allocation, source 4 and target 4 arrays can be copied from one to another using row clone operations, because they reside in the same subarray, they occupy the whole row, and they're not offset at different spots in their DRAM rows. Okay, so we develop the alloc align function, or a mechanism, to satisfy all of these three requirements, to allocate data in a way that these requirements are satisfied. And here are the semantics of it. So we have like it's called like the regular malloc function that you use to allocate virtual memory to your application, and it will try to optimize the physical address allocation such that row clone operations can be used most effectively. And here's an example to describe that. So we have rows that are sized 8 kilobytes, and we want to allocate 12 kilobytes of data. We can guarantee, for example, we can initialize this some parts of this row with like all zeros. If we allocate at least one row in one bank, and allocate the rest from other banks. So if we have an 8 kilobyte chunk that we can allocate to a single row, to a single subarray, then we can initialize this this chunk of the whole allocation easily using row clone operations. But we cannot, for example, initialize this part of the array using row clone operations because it doesn't occupy the whole row, because there's not enough space for it. And we make an observation. So today's system usually have 2 layers of translation between program observed addresses and physical DRAM addresses. And the OS has full control over virtual address to physical address translation, but it has no control over the physical address to DRAM address mapping. The idea here is if we can control virtual address to physical address translation, and we know what the physical address to DRAM address mappings look like, we can implement alloc align function. So how does it work? First, it will try to distribute the array that we are allocating over multiple banks while occupying rows as fully as possible. And it will just fall back to malloc, how malloc works for the remaining data. And we make 2 assumptions. The first one is we know the DDR address mapping, as I described in the last slide. And this, fortunately, this can be reverse engineered. We can so the good thing about this is we only need to know the row addresses that belong in the same subarray. So we can check if row clone operations succeed, and then we can we can form a bucket of those rows that can be successfully row cloned to each other. Or we can do RowHammer, for example, to reverse engineer again the mappings in finer granularity. And there are other ways to reverse engineer this. And the second assumption we make is connected to the first one. So we know which DRAM rows are in the same subarray. And this is already something we can do by just performing row clone operations. And another version of alloc align could be used to implement, to allocate data to make sure that we can initialize it with, this is for, so other versions can be used to make sure that 2 different arrays reside in the same subarray. So for that, we propagate an ID. It's the row, what we call row clone identifier. And the operands with the same ID will be placed into the same subarray. So we can copy one array to another. And here is the configuration of the DRAM module we have. So this is the SODIMM we're testing. This is a Micron chip, and we, as CompDRAM showed, this supports. We also show that this supports row clone operations at like 100% success rate for some of the rows. And we have 16,000 rows in this module, 8 banks, and each column is, so each row is 8 kilobyte size, and the total DRAM size is only 1 gigabyte. And this is what the physical to DRAM address mapping looks like in our system. And this is configurable. We implement a simple mapping scheme. And now I'll describe the allocate align over an example. I have something in the chat. Will we face fragmentation issues allocating memory this way? Yeah, so maybe I can talk about this more in one of the next slides where I describe the structures that we have. I could probably answer it better over there. But can you remind me to actually answer this if I forget? Thanks. So I will describe how it works over an example, and also the algorithm in the next slide, as I just said. In the example, we're allocating two arrays, 16 kilobyte large arrays, A and B. Oh, I guess the chat is blocking your view right now. Okay. And here are multiple DRAM banks in two rows in the subarray, in the same subarray. And what allocaline will try to do is it will scatter contiguous virtual pages into multiple banks to enhance bank level parallelism to streaming accesses, and also make sure that the two arrays can be copied to one another. And to do so, it just overlaps the virtual pages of the two arrays that are at the same offset in the DRAM and then the same DRAM bank. And to do that, we implement some structures. The first one is the subarray mapping table. And this is a table that collects DRAM rows that map to the same subarray under common entries as physical page address pairs. This will become more clear as I describe the structure here. So a table contains multiple entries for each bank and each subarray in the bank. And each entry will store multiple row address pairs physical address pairs that map to a single row in this subarray. And also metadata about how many rows are still not allocated yet. And we assume that the DRAM row to subarray mapping is arbitrary. So subarray 0 could be made out of rows 0, 15, 37, row addresses, row indexes 0, 15, 37, and subarray 1 could be row 13, 22, 156. So even under this assumption, it will function correctly. And we reserve one address pair in the structure for initialization. So we will just reserve this entry and fill the row that corresponds to those addresses with all zeros so that we can bulk initialize data with zeros in the subarray. We have another structure called subarray ID map, and this is mapping from page numbers to subarray indices. And later we will use this to perform bulk data initialization. So how we use the subarray mapping table? When we call the allocaline function, it will operate in this way. So first, it will find how many banks it needs to utilize, and this is to spread the allocation across many banks. And to find this out, you can just simply divide the allocation size by the number of banks you have. Sorry, the total amount of banks multiplied by how much data we can store in one row in that bank. And then we will split this array into 4 kilobyte blocks because 4 kilobyte is also a single virtual page in our system. And we have a parameter named NB. It's the number of 4 kilobyte large blocks in this array. And for all blocks in the array A, until we reach the block in the middle of the array, we pick a bank for that block, and we select an entry from the subarray mapping table, a physical address pair, and then we select one pair from that entry, and then what we do is we map the virtual block at the index we're in to one of the addresses in the pair, and the block that's indexed at this position, so offset by the middle essentially to the other pair. So what this will result in is something like this essentially. What we're trying to do is we split the array into multiple 4 kilobyte pages, and then we have to gather different 4 kilobyte pages at different offsets to the same row, because a row is 8 kilobytes large and then our pages are 4 kilobyte large. So we want to place them together to occupy a whole row. And this is how we do the mapping. Will this result in fragmentation issues? Probably, when you want to integrate it into the body allocator in Linux, for example, or maybe a more sophisticated allocator, what we do is really simple in this implementation. To free these spaces, we need to just manage the subarray mapping table again, give it back the entries that we occupied previously, and then just change the mappings in the page table. But integrating into a real scheduler, or the ones that you would find in sophisticated systems, I think we left it for future work, essentially. And there could be challenges in implementing it in such a sophisticated mechanism. Okay, yeah. And next I'll describe how we do the bulk data initialization. So we call what we call the function RCI, row colon initialize, and the semantics look like this. So it will take a pointer to array A, and then an argument N, and it will initialize A with N bytes of zeros. So what we do is we split again the array A into 4 kilobyte blocks, and we then do the same. We go over the same loop. We iterate all the way until we get to the middle of the array, and we translate from AI to AI's physical address. And we use this as the destination address for the row colon operation to bulk initialize the array. And then we access the subarray ID mapping with PA1 to obtain its subarray ID. So we're trying to find out which subarray this physical address is. So we mapped AI to one physical page in the previous slide, for example, when we called allocaline, but we don't know what subarray that is without accessing this subarray ID map. And once we do it, we know which subarray ID, which subarray it belongs to. So we can now query the mapping table to find the row that was initialized with all zeros. And once we find that, what we need to do is just perform a row colon operation from this physical address that we found that contains all zeros to PA1, which holds the data for the array that we want to initialize. And once we do this, we will have automatically copied the zeros to the 4 kilobyte page offset at this point in the array, because they belong in the same subarray based on they belong in the same row based on the mapping that I talked about in the previous slide. So we don't need to do it twice, basically. Next, I'll talk about the other challenge, which is memory coherence. Now, since row clone and similar work like Ambit, they operate on data that resides in DRAM, and we cannot guarantee that the most up-to-date copies of that data to be in DRAM at that point, because we have caches and we store copies of data in caches. Coherence is a problem for us potentially, and what we do is we implement what's called CLFLUSH in the Rocket core, and this is basically an instruction that we use to flush dirty cache blocks, evict cache blocks back to DRAM. So we guarantee by executing these instructions on the array that we want to bulk initialize or copy, we make sure that the data for that array resides only in DRAM, and there are no cached copies. So the good things about this approach is that it's realistic. These instructions are supported in contemporary architectures, and we get rid of the coherency problem. So reads and writes can still go to the cache for this data that we want to copy. And once we want to copy it, we will flush its cache blocks to DRAM. But the disadvantages are it has very high instruction overhead. So we have to use one instruction to evict one cache block, and there could be many cache blocks in this array that we want to copy. And there are other mechanisms that can be used to alleviate these overheads of CLFLUSH. One of them is the dirty block index. And what this helps with is it implements a structure called DBI. And we can query this structure with a row address. And the structure will tell us which cache blocks of this row is cached. So we need to only run this instruction, execute this instruction for those blocks. Because for others, we guarantee that they reside in the DRAM already. And the other mechanism that can be used is lazy PIM. Basically, the idea here is we are aware that coherence is a problem, and by copying data in DRAM directly without evicting all its cached copies back to DRAM can result in us operating on stale data. But we can understand this afterwards, and only when it happens we will roll back and do the operation again once we have all the data all the data up to date in DRAM. So the key idea of this mechanism is like that. And you can take a look at these papers for a better overview, essentially. And finally, I will talk about how we evaluate. I'll show our results for this use case study. Here's the system configuration we have. We have a 50 megahertz in-order rocket core. It has a 4-entry TLB, a very simple core essentially with small caches, and a gigabyte large DDR3 clocked at 800 mega transfers per second. And it has a single rank. And we test primarily two configurations. The first one is bare metal, so we don't have any address translation at all. And the second one is what we call no flush. It has OS support, meaning that there is virtual memory and all these memory allocation mechanisms are in place. But we assume that data is up to date in DRAM, so we don't run any CLFLUSH instructions yet. And we evaluate these workloads. So we have micro benchmarks for CPU copy and row clone copy operations. And also we evaluate one spec workload on this FPGA platform, libcommon, and we have some results for that. So this one, in this figure, I show you the throughput improvement for copy operations on the bare metal configuration. And on the x-axis, you see increasing array size. And the takeaway we make from this figure is that row clone copy can provide up to 365x performance improvement over Rocket CPU copy for 8 megabyte large arrays. And here we show the throughput improvement again for copy operations, but this time for the no flush configuration. And we have here both row clone initialize and row clone copy bars that represent the throughput improvement for bulk initialization and bulk copy operations. And again, here on the x-axis, you see increasing array size. And the takeaway here is that with system support, RCC and RCI can improve throughput by 119x and 89x. And finally, we estimate the overhead of cache line flush operations. And y-axis here in this figure is the same. We have the throughput improvement for both row clone copy and row clone initialize operations on different bars. And on the x-axis, we have the proportion of the cache blocks of the row or of the data that we want to copy, how dirty they are, basically. If none of the blocks are dirty, meaning that their value in the caches were updated by the processor, so the DRAM device holds a stale copy. It holds no stale copies. Essentially, it's 0% dirty. And if it's 100% dirty, it means that the whole array was cached, and all of the cached copies are dirty, meaning that they were updated. So we need to, when we evict that cache block, we also need to write back the data. The difference between 0% dirty and 100% dirty is only that. So for both cases, we CLFLUSH every cache block. But in the 100% dirty case, that CLFLUSH results in a write back compared to no write backs in the 0% dirty case. And we see that CLFLUSH dramatically reduces the potential improvement of RCC and RCI, or clone copy and initialize operations. And we also conclude that PiDRAM enables better, the study of better mechanisms to alleviate these dramatic reduction in performance in the future. So to summarize, this is something that I didn't show you, but PiDRAM can also run real workloads end to end. So we replaced the calloc calls or calloc calls, which essentially give you so allocate memory for you and initialize it with zeros with allocaline and rowclone initialize functions, and we saw that we could improve its performance by 1.3%. The reason for this very little improvement is because there are little number of operations that we could replace in this workload, and we already see this, but rowclone copy can greatly improve bulk data copy performance with system support by 119x and without system support by 365x. And finally, rowclone requires efficient coherence mechanisms to achieve the full potential of its copy throughput improvement. I'll talk about other case studies that can be done using PiDRAM. So first case study, mechanisms like MBIT and SIMDRAM share similar memory allocation and alignment constraints as the rowclone case study that we did. Similar memory coherence challenges. Exclusive to SIMDRAM, there's also a challenge what we call transposition, because SIMDRAM operates on data that's allocated in a bit so operates data on a bit serial way. So it needs to transpose the operand first before writing it to DRAM cells. So this is another challenge that could be interesting to explore. And potentially other two case studies could be on DRAM latency puff and clock-TRNG. So DRAM latency puff is a physical unclonable function in DRAM. We access DRAM cells with reduced TRCD, and we find that this access results in a signature that's unique for that DRAM device for that row. And this is used in physical this can be used as a physical unclonable function. And clock-TRNG is a DRAM true random number generator. And these have these have challenges about memory scheduling policies. So if you are using DRAM to generate random numbers to store data and to generate physical unclonable function signatures, how do you schedule these commands correctly between the regular read and write requests so that you don't hurt system performance greatly? And both of these works require some sort of post-processing on the data they obtain after performing these operations. So efficient post-processing integration is another challenge for these works. And in the paper, we talk about other case studies that can be done using PiDRAM. So you can take a look at the paper for more of these, more discussion on these. And finally, we have a comparison against relevant other platforms. And we see that compared to existing platforms, PiDRAM enables end-to-end integration of processing using memory techniques by having an interface with a real DRAM device and providing a flexible memory controller design, being open source so that developers can keep improving it, and it supports system software. And we see that other platforms fail to deliver all of these together, basically. I took a lot of time, but I think I'm done with my slides. So this is somehow stale. I won't talk about how to install and use PiDRAM. So if you have any questions, I can take them now. Okay. I guess there are no questions. So I will stop sharing and Hassan can take over.
Thanks for the presentation, Ataberk. Okay, great. Yeah, so we will jump into the project updates. Let me just quickly turn off the